well, rational numbers are really important. We're going to see them all the time, all over the place. And remember, a rational number is simply just a number that can be written as an integer divided by an integer, or an integer over an integer, where that downstairs integer is not 0. So I thought it would be fun to take a look at some examples of numbers and see if they're rational numbers or not by writing them as a over b, where a and b are integers and b is not 0. Let's check out our first one together and see what we think. So the first challenge is to look at the number 4 and 2/3. Well, 4 and 2/3 is actually an example of what's called a mixed number, because you got that integer out in front and you got that little fractional 2/3 thing. So let's see if we can write that as one fraction that's bigger than 1. So let's see if we can convert this into a fraction and see that it's rational. So the first thing to realize is to take a look at it, right? So there it is, 4 and 2/3. Well, actually, just the way I said that, 4 and 2/3. That and means plus. So really, watch this. I'm going to push that 2/3 out, and I'm going to insert a plus sign right in between them. So now we have this addition question, 4 plus 2/3. Well, you know what to do. We have to get a common denominator. So that 4 is really 4 over 1. And now to get a common denominator, I'm going to multiply the numerator and denominator there by 3. So I see 12 divided by 3. Now we have a common denominator, the bottoms agree, so we can just add the tops of those fractions, add the numerators. And so what I see here is 12 plus 2, all divided by 3. And 12 plus 2, we all know is 14. And so we see the answer is 14 divided by 3. And since that's an integer divided by an integer over an integer, 12 over 3, and that 3 is not 0, it is rational. All right, let's take a look at another one. This one's a decimal. So 0.25, or how you might say it is 25 100ths. Well, it turns out that this also is an example of a rational number. And the way to see this is to really kind of speak it correctly, which is 25 100ths. And so if we think of the place value of that 5, we see it's in the hundredth spot. And so we can actually write that with a denominator that's a power of 10. In this case, the power of 10 would be 10 squared. So we'd see 100. So in fact, we'd see that 0.25 is really equal to 25 divided by 100, or 25 over 100. Integer divided by an integer over an integer, it's a rational number. So even 0.25 is really a rational number in disguise, because we can write it as integer over integer. All right, how about a friendly, familiar number like 26? Well, 26 actually is also an example of a rational number, because 26 can be written as 26 over 1. You can always write a number with an invisible over 1 there. So in fact, 26 over 1 is written in the style something divided by something, where the somethings are integers. So therefore, even 26, familiar 26, is really an example of a rational number. And finally, let's take a look at negative 15. So what about negative 15? Well, again, it's the same trick. We can always write invisible over 1 in any number we want. And since negative 15 is an integer, then when I write it over 1, which is also an integer, I see negative 15 over 1, integer over integer. Bottom integer is not 0, and so therefore we see it's another example of a rational number. So negative 15 is actually a rational number, because I can write it as negative 1. Rational numbers are abound, and even numbers that we know and are familiar, we can see by rewriting them really are rational numbers. Enjoy thinking about the rational numbers in your life, and I'll see you soon. As we're seeing, there's lots of different types of numbers. We've already seen whole numbers. Those are the numbers that we count with, including 0. We've seen integers, which are the whole numbers along with their opposites, the numbers with the negatives in them. And then we're now thinking about rational numbers, which are the numbers that can be written as a over b, where a and b are integers, and b is never 0. So let's actually see how we can look at all these numbers together. They kind of fit together nicely, and we can what's called in mathematics a Venn diagram to actually see that visually. So a Venn diagram is just a really cool way. Put one kind of there, big old blobs, and then you can put blobs inside of blobs to show that the stuff inside the little blob is also something that's part of the big blob.
So you can have
things
kind of more refined.
So for example, with the numbers that we've been thinking about recently, the biggest blob we can think of right now are rational numbers.
They're kind of all encompassing
big blobs.
And then there's an inside, more refined version of rational numbers, which we actually saw together,
which are actually called the integers. The integers, remember, are special cases of the rationals because the integers, after all, can be written as that integer over 1.
And then inside the integers,
we have the whole numbers.
The numbers
that aren't the negative ones, just the positive and 0 ones.
So we could put
another little blob inside to actually indicate
the whole numbers.
So let's just have some fun by looking at certain numbers and seeing exactly where they fit in this Venn diagram.
Which little blob do they go in?
So let's start off with the number negative 12.
All right. Is
negative 12 a rational
number?
Can I write it as
a over b,
where a and b are integers?
Well, of course.
Negative 12 is an integer, so I can write it as negative 12
over 1.
So therefore, we see that it's a rational number.
Awesome. Now, is it an integer?
Well,
absolutely, because it's the negative. It's the opposite of 12,
and 12 is just a regular old-fashioned whole number.
So in fact, we see
this is an integer. So we can push negative 12. Watch, I'm going to push it down even deeper into the Venn diagram to the integers blob.
Can we push
it all the way down to the whole numbers blob?
Well, check it out.
Negative 12
is actually the opposite
of 12. It's a negative number, and whole numbers are not negative. So in fact, we can't push it into that elite club. That club is too elite.
This negative 12 just makes it to the integers. Isn't that fun? Let's try another one.
How about 0.4?
Or the way we read that is 4 tenths. Well, just by saying 4 tenths, it actually gives us a clue that we can write it as 4 over 10. So we can convert that decimal expansion of the number actually to a number that is now easy to see to be rational, namely 4 over 10. Now, 4 over 10 is an example of a rational number.
So we definitely makes it into the first club.
Can it go deeper?
Well, is it an example of an integer?
Well, sadly,
no. It's not an integer.
You see why?
Because it's not one of the numbers that we would see as a whole number or the opposite of a whole number.
It's actually between
two whole numbers. It itself is not a whole number. So it can't even make it down into the integer category. It's stuck at that top category of rational numbers. It can't go any deeper.
How about the number
11?
Well,
11 is certainly a rational number because I can write it as 11 over 1.
So that's easy
because 11 itself is an integer.
So it's definitely
a rational number. So we're in the game.
Can we go deeper?
How low can we go? It's almost like limbo.
Well, 11 over 1 is a rational. 11 itself, of course, is an example of an integer. So it actually makes it into the integer category. And in fact, it's a positive integer. So it makes it all the way down into the whole number category. It made it to the absolute most elite part of our Venn diagram. It's an example of a whole number, so I'm going to put it right there. And finally,
let's take a look at negative 2/3 together.
Well, negative 2/3, we can see immediately that it is a rational number because I have it as negative 2 over 3, and those are both integers where the 3 is not 0. So we definitely
make it into the first category, into the rational blob.
But can I go any deeper? Sadly,
no. It's not an integer.
For it to be an integer,
we'd have to be able to write it as that over 1, an integer over 1, and negative 2/3 is not an integer. So it can't even go into the integer category. There's no need to even think about the whole number category because we know the game's over. It's stuck in the rational category and can't go any lower anymore.
Anyway, you can see how we can classify different types of numbers.
The beauty of looking at numbers and seeing their structure is to see the different types of numbers that are around us, and the Venn diagram is a powerful way to actually visualize where we are in our world of numbers.
Have fun thinking about numbers on your own,
and we'll see you soon.
lot of times we'll be looking at numbers and we'll want to consider the opposite of a number. Now, you know the word opposite, but in math, the opposite of a number is a really, really well-defined thing. The opposite of a number is very, very simple. If you visualize that number on a number line, then the opposite of the number will have the same distance away from zero, but in the opposite direction. That's why it's called the opposite.
I thought we'd take a look at an example
where we can see the idea of an opposite together and actually visualize what opposite looks like in a real world, actually high finance example. Let's check it out. So here's the challenge.
First of all, some interesting fun facts.
Until June 24th, 1997, the New York Stock Exchange priced the value of a share of stock in eighths. Kind of cool, isn't it? Such as 27 and 1/8, or 41 and 3/4.
The change
in
value of a share of stock
from day to day
was also represented
in eighths
as a positive
or negative number, depending upon whether the price went up, that would be positive, or down, in which case it would be negative.
Okay, so that's some fun facts.
And so now let me just take all those fun facts, and I'm going to push them right over my head. Watch this. There it is. There's a fun fact. You can just have them over my head.
The table that you see here actually shows the change in value of a stock over 2 days. And here is our challenge.
Our challenge is to graph the change in the stock value for Monday, and then graph
the opposite
number on a number line.
And just for fun, I
thought we would use a vertical number line. Now we're all used to seeing number lines that look like this. Check this one out. See?
Right? And then I can put the numbers in.
And then I can put the numbers in, right? 3, 2, 1,
0,
and so forth, all the way down.
And you can put the negative numbers in,
and you can put the negative numbers in, too. -1, -2, -3, and so on. So it fills it all up.
But how about a vertical
number line, just to mix it up? So I'm going to put this on its side. Now remember, the positive values go up, so when we turn it, you can see that we have now 3, 2, 1, 0, -1, -2, -3. And that's always how vertical number lines look, even though we haven't seen too many of them.
And now we want to take a look at
Monday, and let's take a look at the change in value for this particular stock, and we see -3/4, which means that the price dropped. It went down. That actually gives us a hint what direction we're going to go to. Down. Negative, and the number is -2 3/4. So -3/4 is a number that's between -2 and -3.
It's pretty negative.
It's actually going to be a little bit closer to -3. So when we actually plot that point, I put it right there.
Now, to figure out the opposite number. Well, what I do is I look for
a number whose distance away from zero is still
2 3/4. But now in the opposite direction, which means now we go up. So we're going to go up 2 3/4 from 0. So this number is going to actually be between 2 and 3, and again a little bit closer to 3, and there it is. And you can see that value, which is actually 2 and 3/4, is the opposite of -2 and 3/4. The opposite of the change in the stock value for Monday is actually 2 and 3/4. And we can actually see it visually by looking at this neat little vertical up and down number line. So the important thing to remember is that the opposite of a number means it's the same distance away from 0 as that number on a number line, but in the opposite direction. Have fun thinking about opposites. Remember, they attract.
And I'll see you soon.
The absolute value of a number is merely the distance between that number and 0 if you were to plot it on a number line. Let's take a look at an example.
Let's take a look at an example and see absolute values
in fact, this is going to be
a cold absolute.
So I've got a little table here that actually shows the average low temperatures in December in one location during a 4-year span.
So you can see all 4 years, and you can see the low temperatures.
Our challenge is to find the absolute value
of the average December low
in the year 2011. So check out the chart, and you can see all 4 years there. And 2011 is that one way over there. You can see it, and you can see what the temperature there was, the low temperature. It was negative 1.2 degrees Celsius. So we have to first of all plot negative 1.2 on a number line. And again, I just thought it would be fun to use a vertical number line. So there it is. There's a vertical number line, and I label it.
3, 2,
I'd say
1,
3, 2, 1, 0, negative 1, negative 2, negative 3. And now what I'm going to do is I'm actually now going to plot the point negative 1.2. So where does that live? Well, it lives between negative 1 and negative 2, and it's actually going to be a lot closer to the negative 1 this time, because the rational number negative 1.2 is actually closer to negative 1 than it is to negative 2. So I'm going to put it right there. So there it is. You can see it.
And so that represents that value.
What's the absolute value? Well, that represents just the distance between that point and 0. And so if we look at that point and 0, we see what that distance is, which is 1.2.
And so the absolute value of negative 1.2
is 1.2. Here's a way of thinking about it. In fact, this is a kind of a little sneaky thing. It's between you and me.
It's measuring length.
It's measuring length. Absolute value is measuring length. And if you take out a ruler and look at a ruler, you will never see negative numbers on the ruler. It starts at 0 and then goes up. And that's why the absolute value of a number will never be negative. It's always going to be positive or maybe 0. And so that's a way of thinking about it. It's distance.
So in our example, however, what we can see is we can actually write the absolute value. And the way we write it is we use these vertical lines.
We nestle the number in between two vertical lines, and that means absolute value. So when I write that, it means the absolute value of negative 1.2, and we've seen what the answer is. It equals, boom, ta-da, 1.2. Kind of a little between us. You're taking the absolute value of a negative number. All you got to do is strip away that negative sign, and that's going to give you the absolute value. And if you're taking the absolute value of a positive number, there's nothing to do. The absolute value of a positive number equals itself. How cool is that? Absolute values allow us to see the distance. A point is
Enjoy
from
thinking
0.
about absolute values.
Enjoy thinking about absolute values even in cold
I'll see you soon.
I'll see you soon.
Suppose that you want to take a list
of numbers and order them. Well, here's 3, 0.4,
1/3, and 0.39.
And 0.39.
I want to order them from smallest
to largest. Now, how am I going to do that?
What I'm going to do
what I'm going to do is first convert everything to a decimal. That's the best way to compare these numbers. I can compare these numbers pretty readily, but that one's a fraction. So first, let's do a little side calculation.
Let me just cut them up so I can move them around.
Let me just cut them up so I can move them around.
Decide how we want to order them.
Let me decide how we want to order them.
So first, let's actually figure out
the
decimal equivalent to 1/3.
The decimal equivalent to 1/3. So I take 1 divided by 3.
0.
0.
Subtract, I get a 1. Bring
I get a 1. Bring down a 1. So I bring down a 0. I see 3 goes into 10 3 times. 3 times 3 is 9. Subtract, I get a 1. This is deja vu again.
I'm going to see the 10 again. So
I see the 10 again. So that's going to be a 3 again. That's going to be a 9 again. I subtract, I get a 1 again. I see this repeats forever. So I see that 1/3 has an equivalent decimal expansion to be equal to 0.333 forever. Is that really true?
Sure is. There it is. So
there it is.
So now
that's pretty cool. So now that we have a decimal,
we can actually order them.
Order them. How do you order? Well, we start the furthest left and look for the greatest
to find the biggest
digit
number.
to find the biggest
everyone starts
number.
with a 0.
So everyone starts with a 0. So they all tie there. Now we'll go to the 10th
This is a 4, that's a 3, that's a 3.
4, that's a 3, that's a 3. These guys tie, but they're both 3s. That's small in the 4. So this is the world's champion. That is the biggest. Way over here.
Now, what about the rest?
Now, what about the rest?
Say, hey, wait.
You see, some people might say, hey, wait, there are sort of an endless run of 3s, so that's much bigger. But no, we start from the left and we systematically look for the biggest digit. So they tie here. But the moment I go to this digit, I see a 9, and here I see a 3. Doesn't matter what the other digits are. The game is over. The 9 wins, and in fact, this is the next biggest one.
And finally, this is the smallest one.
And finally, this is the smallest one.
If we want to sort of plot this on a number line,
we can do it.
we can do it. We can do it. I'm going to enlarge the number line. I'm going to enlarge the number line to show lots of detail here. In fact, I'm just going to show you the number line from 0.3 to 0.4. So this is a real close-up into the number line. Well, where are these numbers? All right. Well, where are these numbers? Well, 0.4, that's pretty easy. 0.4, that's pretty easy. It's literally right there, right? So that's pretty straightforward. And 0.39 is going to sort of be 1/100th away from there. So it's going to be really close. I can't even show it to you. My picture's not going to be accurate enough. I got to slide that over a little bit. It's going to be really close to there. Right around here. So that's really close. Okay, so that's really close. 0.333 is going to be, well, around here. Remember, that number was actually the decimal for this. And so we see the numbers kind of look like this on number line. This one is kind of around here. This number is kind of around here. And this number is right there. So there, I'll put my fingers on roughly where the placement of those are. And you can see the ordering of them, though. 1/3 is the smallest. Its decimal is 0.333 forever. The next largest is 0.39. And then the largest one out of these three is 0.4. So you can order numbers. You can look at them. The decimal expansion is an easy way to be able to compare numbers. Actually, I think easier than looking at the fraction expansion when these numbers actually can be expressed as a fraction. So decimals are really handy. Being able to convert things into decimals, awesome. I'll see you soon. Hey, let's put all these ideas together. And see how we can actually order decimals and fractions together. And one way of doing it is just to literally plot those points on a number line. So here's a bunch of numbers. 1 and 3/4. Negative 0.6. 0.5. 0.55 repeated. So 0.555555 and so forth. Well, plotting decimal numbers are really easy because this is the real number line. But with the fractions, it might be easier to first convert them to their analogous decimals. So let's do that first. What is 1 and 3/4? Well, 3/4 is 0.75. So 1 and 3/4 is 1.75. So 1.75 is located where on the number line? Well, here's 0, here's 1, here's 2. This is 1.75. This is 1.5. 1.75 is halfway between 1.5 and 2, so it's located right here. So right here is 1.75. Let me actually cut that out there. So I'll put it right in the spot. And I'm going to convert this 1 and 3/4 to 1.75. So then I see negative 0.6. Where is that? So that's negative 0.05. So negative 0.6. So negative 0.6 is a little further to the left of that. So it's, let's say, right here. And so this is negative 0.6. So put that right there. And then I have 4/5. And then I have 4/5. The same thing as 8/10. Multiply the numerator and denominator by 2. And so 8/10. That's pretty easy. That's just simply 0.8. So 0.8 is something a little bit less than 1. Maybe right here. 0.8. And then what about 0.555 repeating? Well, of course, that's something that's a little teeny bit bigger than 0.5. 0.5 is here, so this is a little bigger than that. And this is 0.55 repeating. And now you can see I can read off the order by starting from the left and just moving it like it's numbers. So I first hit 0. So negative 0.6. The next thing I hit is 0.55 repeated. The next thing I see is 0.8. And the next thing I hit is 1.75.
The next thing I hit is 1.75.
So that's the order of them.
So that's the order of them.
What exactly are they? Well, I have
what exactly are they? Well, I have
-0.6.
negative
0.55
I have
repeated.
0.55
I have this
repeated.
number,
I have
0.8,
this
which I
number,
remind you is just
0.8, which I remind you is
4/5.
just
That's how it was given to
4/5. That's
and
how it was given to us.
1.75,
And 1.75, I remind you, we converted that from 1 and 3/4.
So in fact, here is the ordering
of these numbers from smallest all the way up to largest.
Neat. Anyway, taking fractions and decimals,
fractions
and
and decimals,
compare which is
and being able
larger
to
and being able
compare
to
which
actually
is
order
larger and being able to actually order them is a really important skill. We're trying to see which is bigger than something, which we're always doing.
With fractions,
it turns out that with fractions, getting a common denominator is a wonderful way of actually then comparing the numerators to see which fractions are larger, or expressing everything in terms of decimals, putting them on a number line, and just reading from left to right. I'll see you soon.